Hello, everybody. So today we are starting section 4.3. We're actually only going to do part of 4.3, and then in the next lesson, we're going to finish 4.3 and cover 4.6. So just so you have a heads up of what's coming. So today, the section that we're focusing on is the section that's all about Riemann sums. Now, Riemann sums it's basically what we did last class when we were calculating area using rectangles. We're just going to expand on that concept. So you'll see here that we have a, new sort of summation. So I'm talking about right here. So this is just saying that if you have a closed interval a to b and your function is defined on that interval, you can partition it. And in this now, the difference is that the partitions, they don't actually all have to be the same size. So that's what this note says right here. It's not necessary to have all of the subintervals be the same width. If we do it that way, it does make computation a bit easier, a little bit more simple, but it might not always give the best approximation. So I just want you to know that we can break up our subintervals so that they are not all the same width, and we will practice with that today. Okay, so what is this little formula telling us? Well, we have the sigma here, so that's telling us to add them up. So this is saying add areas of all the rectangles. And then this f of c sub I is representing the height of the rectangle. Right, so the f of whichever point you pick, the point has to be within the interval, within the subinterval. So that's what this part's talking about. It's just saying that that value c has to be in the subinterval that you're dealing with. And then this last piece, the delta x sub I is the width of the rectangle. So it looks very similar to the formula from last class. Basically, this definition is just set up a bit differently because not all intervals have to be the same width. So we're going to do quite a few examples today, just practicing with this concept, and we will practice kind of like looking at what the graphs look like, looking at doing it from equations and even tables. So this first example says use left and right Riemann sums to approximate the area onto a curve of f of x equals 1/4 x squared plus 1 on the interval 0 to 4 using 3 subintervals, and those 3 subintervals are given. And so one thing you do want to check, I would always check, are my subintervals all the same size? And here 0 to 1 is size 1, but 1 to 3 is size 2. So these are unequal subintervals. Okay, I put the graph of this function on the paper so that we can kind of like compare the graphic way of doing it with the algebraic way of doing it. But you don't always have to graph them. It can be a helpful visual though. So let's do the left Riemann sum first. So left Riemann sum means that the left endpoint of the rectangle touches the curve. Okay, so what do I mean by that? Well, first of all, we have our interval 0 to 4. So this is the interval we were supposed to look at. And then we have the 3 subintervals. So I'm just going to make little tick marks. We had 0 to 1, 1 to 3, and then 3 to 4. So those are our 3 separate intervals. And so here for the left Riemann sum, we want the left end of each of these intervals to be where the rectangle touches the curve. So here's how we're going to do it. You're going to pick the left point of the interval. In this case, it would be 0 for the first interval. Touch the curve, make a rectangle. Then we need to do the same thing here. This is the left endpoint of the second interval. Touch the curve, make the rectangle with that height. And then one more time, touch the curve, make the rectangle. So that is how we do our left Riemann sum. So the left side of the rectangle is touching the curve. And so if we want to find this sum, all we have to do, I'm writing a capital S and then it's a capital L, but a subscript L to show that it's the left sum. So we just need to take the width and then multiply it by the height. And so the first interval is a width of 1. And then this height right here, well, we can see that that's a 1, but I also want to think about how to do this if we didn't have the graph, right? So if we didn't have the graph, what you would be looking at is this. These are the left endpoints of the interval. So what we're doing is we're having 1 times f of 0, right, the y value at the x value 0, plus the width of the next interval is 2 times the height of that one. The height of that one is going to be, so this y value here is going to be f of 1. And then the last interval has a width of 1, and it has a height of f of 3. And so because we have the function here, we can find what f of 0, f of 1, and f of 3 are. And so that's what you want to do next. So here, f of 0 is just 1. F of 1 is going to be 1/4 plus 1, which is 5/4. And then f of 3, 3 squared is 9. 9 times 1/4 is 9/4 plus 1 is going to give us 13/4. And then you would add those up. I'm going to skip that part for now. And looking at this, we can see that these rectangles here are, so the areas of these rectangles are underestimating the area under the curve because we are missing a few regions. So this is an underestimate. Okay, so now let's try the right Riemann sum. So here we're going to use our right endpoints instead, which are going to be 1, 3, and 4. And so making my rectangles, I'm going to come up. I have this point and make a rectangle. And then we have 3, come up, come over, make the rectangle. And then 4, come over, make the rectangle. And so here we can see that the area of these rectangles is going to overestimate the area under the curve. Oh, I guess I should, okay, hold on here. We'll write this. Right Riemann sum means that the right endpoint of rectangle touches the curve. Okay, now let's do the calculation. So still that first one has a width of 1. That's the size of the interval, but instead of f of 0, it's going to be f of 1. We're using all of the right endpoints. And so here we end up with, and that's 5/4. F of 3 was 13 over 4. And then f of 4, let's see, 4 squared is 16. 1/4 of 16 is 4, plus 1 is 5. And so this here would give us an overestimate. And so the actual area would lie somewhere between these two values. Okay, let's try another one. Find the left and right Riemann sums for the function f of x equals 4 minus x squared on the interval 0 to 2 using 4 equal subintervals. So here we are being told to use 4 equal subintervals, which means we want to do what we did last class. We want to find what the size of each of those intervals is, and we do that by taking the b minus a and dividing by the number of intervals. The b minus a, those are the endpoints of the interval, and then we have 4 intervals, and so we're going to have these be size 1/2. So let's write them out. I like to write them out. 0 to 1/2, 1/2 to 2 over 2, 2 over 2 to 3 over 2, and then 3 over 2 to 4 over 2. Okay, and then let's draw them out, draw the rectangles out, and then we'll calculate them algebraically. So to draw them out, well, first I'm going to need to put in my endpoints of each subinterval. And so this one will do left and this one will do right. We'll use the same colors. Let's see. Okay, left. So for the left ones, remember we're looking at all of the left endpoints, which are the 0, the 1/2, the 2 over 2, and the 3 over 2. And we're going to use those values to form our rectangles. Oh. Okay, so it's going to look something like that. And we can see that this area is going to be an overestimate. So let's find it. Okay, so here I'm going to do it how I did last class. So because they're all the same sized interval, to make the computation a bit easier, you can leave the 1/2 out front. The 1/2, remember, that's the size. Oopsies, I want the highlighter. That's the size of the interval. So we can leave that factored out front instead of putting it in front of each term. So now we're going to have f of each of these left endpoints. F of 0, f of 1/2, f of 2 over 2, and f of 3 over 2. Right? Or you could write it as 1/2 f of 0 plus 1/2 f of 1/2 plus 1/2 f of 2 over 2 plus 1/2 f. But because they all are just a 1/2, I like to leave that out front. And so I think what you get, right, so just use the function. Hopefully I did this right earlier. And this should give us 6.25. Okay, now let's try the right. So we're going to use all of the right endpoints. Notice the 2 is equal to 0, so that ends up not being a rectangle at all. So this would be this area, which is going to be an underestimate. Notice that in the first example we did, the left gave us an underestimate, versus in this one, the left is giving an overestimate. And then in the first one, the right was the overestimate, and now the right is the underestimate. I encourage you to pause and think about that, why it got switched. Okay? Like, what would tell us right away if it's going to be an over or an underestimate? Okay, I'm going to continue. So we have 1/2 here, and then we're going to use all of our right endpoints. And you would calculate each of those using the function. And I believe what you get is 4.25. And so we can see that 4.25 is indeed less than 6.25. And so the actual area is going to lie somewhere between those two values. So the question is there a better way to approximate? And the answer is yes. Oftentimes, the midpoint will be better. So instead of choosing the left endpoint or the right endpoint, you can choose the midpoint. So here we have the same curve, and then we're showing here that these left endpoints are touching the curve, and this one, the right endpoints are touching the curve. And in this last one, it's the midpoint of each interval that is touching the curve. So we're going to use the same problem now, and we're going to use the midpoint Riemann sums to approximate this area. So it's the same function as before. That way we can compare it. Okay, so let's draw in our 1/2 and then our 3/2. And so, okay, this one's going to be a little bit harder to draw. So we want to pick, okay, we're going to find the halfway between the 0 and the 1/2, and then that's what we're going to use. Just do your best here. That's going to be the height that we use of the rectangle. Okay, so then we'll choose halfway between 1/2 and 1. And we're going to choose that height. Then we're going to choose halfway between 1 and 3/2. And then we will choose halfway between 3/2 and 2. And so it ends up looking more like that. And so we can see here that it does appear to be a better approximation, right? It's not, see how much was missing here in the right one? There was a lot of missing space, and in the left one, there was a lot of extra. And here there's less extra, less missing. So this one is looking better. But let's see. Okay, so I'm going to write out the intervals once more. Oops. And so for the midpoint here, right, halfway between 0 and 1/2 is 1/4. Halfway between 1/2 and 2/2 is 3/4. This one's going to be 5/4. And this one will be 7/4. And so when we do the midpoint Riemann sum, these intervals are all the same size, so I can leave that 1/2 out there. And then we're going to do f of each of the midpoints. And if you calculate each of those, I believe you end up getting 5.375. And so this is the best estimate out of the ones that we have, right? So before we had 4.25 was an under, 6.25 was an over, and 5.375 is a better estimate. Okay, so this next piece is talking about what I asked you to think about earlier, like how could we tell if the left or the right will be an over or an under estimate? And there's a little chart here for you. So in the top two, those are both left Riemann sums. Okay, and so with the left Riemann sums, we can see that if we have a function that is increasing, right? If the function is increasing, those will be underestimates. So if we have an increasing function, the left Riemann sum will be an underestimate. If we have a decreasing function, the left Riemann sum is going to give an overestimate. And then the opposite is true for the right Riemann sums. If we have an increasing function for the right ones, we are going to end up having an overestimate. And if we have a decreasing function with right Riemann sums, we will have an underestimate. That should always be pretty obvious to you if you just sketch the function. But if you don't sketch it, then you might have to think about it algebraically. Okay, so the last piece here is just talking about how to calculate Riemann sums using tables. So here, instead of being given the equation, we are being given certain values of the function in a table. So let's do this. Okay, here we go. Find the left Riemann sum using 6 subintervals. So we're going to find the left one. Sorry, I just want to see what color. Okay, the orange. Okay, so, well, okay, what are the intervals going to be? Well, it looks here like this is already naturally broken into 6 subintervals. So the first one's going to be 0 to 20. The next one would be 20 to 40. Then 40 to 60. 60 to 80. 80 to 100. And 100 to 120. And that right there is 1, 2, 3, 4, 5, 6 subintervals. And notice they are all of the same width. So here these are equal subintervals. And the width of them is 20. And so for this one, we can leave that 20 out front. And we're calculating the left sums. So we're doing all of these left endpoints. So it's going to be 20 times this whole quantity. F of 0 plus f of 20 plus f of 40, f of 60, f of 80, f of 100. And then find each of those using the table. So f of 0 is 1.2, f of 20 is 2.8, 4, 4.7, 5.1, and 5. Whoa. Plus 5.2. Okay, and then please use the calculator. You're going to get 460. Okay, right Riemann sum now. Only difference here is which midpoints you are using. So it's going to be very, very similar with this 20. Instead of starting at f of 0, we're starting at f of 20. Use the values in the table. Okay, so use table values. And you're going to get here, let's see, 532. 532. Okay, and now for this last one, find the midpoint Riemann sum. So find the midpoint Riemann sum using 3 subintervals. So notice it changed. And it changed for a reason. And that's because if we were using 6 subintervals, we don't know the midpoints from this table, right? Like the midpoint of the first interval would be 10, and we don't know f of 10. So that's why it's 3 subintervals. So we're going to divide. We have 0 to 120 right now. We're going to divide that into 3 subintervals, okay? So they're each going to be a width of 40. So 3 subintervals is going to give us 0 to 40, 40 to 80, 80 to 120. Those are the 3 subintervals. And then we need to know the midpoints of them. And so the midpoint here is 20, the midpoint of this one is 60, and the midpoint of that one is 100. And so for the midpoint sum, remember the number out front, these are all the same size. They're all size 40. That's the number that goes out front. And then we're going to have f of 20 plus f of 60 plus f of 100. That gives us 2.8 plus 4.7 plus 5.2, and that should give you 508. So notice this midpoint one is ending up between the left and the right Riemann sums. Okay, one more problem. What if we are given a table and they don't end up being the same size intervals? So here we're being asked to use 5 subintervals, and so I can see that this will naturally break into 5 intervals, right? Because this would be 1, 2, 3, 4, 5. So there are already 5 subintervals, so let's write them out. We have 0 to 3, 3 to 4, 4 to 6, 6 to 7, 7 to 9. Now here, these are not all the same size interval. They are different sizes, and so you just have to be careful when you're calculating the sum. So for the left sum, we're going to have all of our left endpoints, but since they're not all the same size interval, you have to write the number out front. So you're going to do, the first one is size 3, so you're going to do 3 times the left endpoint, the left endpoint f of 0, plus the next interval is size 1 times f of 3. The next one is a size 2, and then we'll have f of 4. The next one is from 6 to 7, that's 1. And we'll have f of 6. And then the last one, 7 to 9, is a width of 2, and that will be f of 7. And then you just go for this. Use the table. F of 0 is 3. F of 3 is 4. F of 4 is 5. F of 6 is 7. And f of 7 is 8. And I didn't calculate this, but go ahead and do that. And then the last one, this one, I'm just going to do the first step of this one. For those of you who feel like you need to see it, you're just going to use all of the right endpoints, but not much else will change. So each interval is still going to be the same width. Like the first one is still a width of 3. Instead of f of 0, we have f of 3. The next one is a width of 1. Then we have a width of 2, a width of 1, and a width of 2. And then just use the table to get those values and calculate them. Okay, so your homework is just a handout for section 4.3. There will be a 4.3 web assign, but it will come with the next homework assignment when we cover the rest of 4.3 as well as 4.6. So thank you for watching this, and I will see you soon. Bye.